Okay guys, let's talk about this. So this is what's called the normal distribution or the Gaussian distribution, and it's a curve that looks a little bit like that. We want to find out the area under the curve, okay? So we want to figure out an integral from negative infinity to positive infinity over g of y dy, okay? And let's call that to be I. Now, don't get worried about this y. It's also equally valid to say integral from negative infinity to positive infinity g of x, as long as you remember to put the dx right here. Okay? Now, here's how we're going to do this. First step, consider I squared. So you have I squared, right? You have I squared, and this is going to be equal to I times I, right? And just to show you that it doesn't matter, if you use x or y, for one of these i's, I'll use the y definition. So g of y dy, and then for one of the x's, for the other I, I'll use the x definition. Okay. Now we see that we have two of these, and they're completely independent from each other, and they're being multiplied. So we could actually just multiply these guys and then put them inside a double integral. Like this, and then I'm just going to do g of x, g of x, g of y, and dx, dy, okay? And then one way you can think about this is that this g of x is this g of y is a constant here. You can pull it out, and then this integral becomes a constant, so you can pull it out, okay? So this does, in fact, equal to that. Now, let's go ahead and plug in our g of x and our g of y, and we get ourselves a double integral. And then, instead of writing all this, I'll just write c for the Cartesian coordinates, because we're using x and y. And then we're going to say e to the negative x squared, e to the negative y squared, some dc, some small region in the Cartesian coordinates. And now we can use our exponent rules to go ahead and combine them. And then I'll put a negative out here. Okay, so why is this useful? Well, notice this looks a lot like the distance formula, or maybe even the Pythagorean theorem, right? And the reason why I sort of contrived this with x and y is so we can use that. We're going to convert this from Cartesian coordinates to polar coordinates. So let's do that. Okay, so I want to go from Cartesian to polar coordinates. So how are we going to do that? Well, we can define some r to be square root of x squared plus y squared, obviously. And then we can go ahead and square both sides. Okay, so now we have that. And then we can describe some coordinate plane where you have these different radiuses. And then, but now you're stuck on a line. So what you do to reach the x and y, you draw circles. So we're going from this sort of plane into here with some angle theta and some radius r instead of some x and y, okay? And for our purposes, theta doesn't matter, because I'll just write down some formulas, okay? So, some formulas are dc is actually going to be r dr d theta, and that's pretty much it. Let's go. So, we're going to convert it. So we're going, instead of going from c, we want to go over the polar plane. And the idea for the polar plane is that r goes from 0 to infinity, because it could be any radius from the origin, and that theta, our angle, comes from 0 to 2 pi, so the entire circle. And now that we have these, we can go ahead, 0 to 2 pi, 0 to infinity, and then we get e to the negative r squared, and the dc turns into an r dr d theta. Okay, so why did we do that? It seems like we made the problem more complicated. Well, actually we sort of didn't. Let's talk about this. Notice, this r right here has the same functional part as the derivative of this. So let's talk about that. So let's take a derivative with respect to r of our e to the negative r squared. Well, let's see. You have your e to the negative r squared, but then you want to multiply it by the derivative. So the derivative of negative r squared is negative 2r. Now, how do you go from this to this? Well, you divide by negative 2, right? So let's see. Negative 1/2 times d dr e to the negative r squared is going to be negative 1/2 e to the negative r squared times negative 2r. And negative and negative cancel, 2 and 2 cancel, and we get r e to the negative r squared. And you see that's the same. So we can go ahead and just make this. We're going to move the negative 1/2 to the outside. And we're going to say it's a double integral from 0 to 2 pi, from 0 to infinity, of the derivative of our e to the negative r squared. And now you can go ahead and use our fundamental theorem of calculus. I'll go ahead, continue this on the right side right here. So let's see. We can go ahead, the integral and the derivative cancel out, and what we get is minus 1/2 integral from 0 to 2 pi of e to the negative r squared going from 0 to infinity. Okay, plugging in, d theta right here. Okay, so plugging in 0, we get e to the 0, which is just 1. So you know there's a minus 1 right here. And then now plugging in infinity, we get e to the negative infinity. And what is e to the negative infinity? Well, it actually doesn't make any sense, but when you're talking about infinity, it's usually a limit. So e to the negative infinity, well, just talk about infinity as just some giant number. And this is going to be 1 over e to some giant number. And this is pretty much 0. It's like really close to 0. And the thing is, when this number gets bigger and bigger, this gets closer and closer to 0. And so it's just 0. Okay. And now we go ahead, plug in 2 pi into this, and we get negative 1/2 times 2 pi times negative 1. Okay, and this just turns out to be pi. But notice, what are we doing? We're actually solving I squared, right? And we're not solving I. So this is actually equal to I squared. So the idea is that you solve for I, which indeed is an integral, it's our original integral, negative infinity to infinity, to infinity of our e to the negative x squared dx. This turns out to be square root on both sides, square root of pi. Okay, so there we go. That's our Gaussian integral right there. And that means the area, this will just draw a little picture. The area under the curve is square root